Section 3.1, this is exponential functions and graphs. First example I have written here, it's the same one from your notes. I'm just going to go ahead and set up a table, and I like hovering around the origin for the most part. So I think I'm going to choose -2 to +2, and then start performing our transformation like we did in the previous chapters. Okay, so I set up my table from -2 to +2, but taking a look at this function, the first thing that I want to do is probably rewrite it in our form. So factor anything off of the x, and I would also like to identify what the mother function of this is. So I think I'm going to do those two things now. So if you would like to pause, now would be a great time to see if you can put it in the mother function in the form that we want it in and identify what the mother is. So I've rewritten the equation in our form, just factoring out a 1, didn't really do much of anything to the x's at all. And I went ahead and highlighted in yellow what the mother function is. Now if you take a look above my table, I have my mother function identified as 2 to the x. So what I'm going to do is I'm just going to go through and keep putting in these x values repeatedly. Now normally I would start at the -2, but whenever I do exponentials, I actually like to start at the positive exponent, because then I can use that property of negative exponents really just mean the reciprocal of if it was positive. So if I do 2 squared down here, I know that that's going to give me 4. Now, if I go back up to the 2 to the -2, that negative exponent just tells me to take the reciprocal of 2 to the +2. So that means that this is going to give me a 1/4. Then I can go through and do the exact same thing with the 2 to the 1. That's going to give me 2. And then if I go up to 2 to the -1, that's just going to give me the reciprocal, which is a half. And then the last one I'm going to have is 2 to the 0, which we know almost every number to the 0 power is just going to be 1. We'll talk about 0 to the 0 next year in calculus. So now let's go ahead and set up our table. We've been doing transformations for a while now, so now would be a good time to pause and see if your table matches up with what my table is going to be. So I've got my table set up now. Looks like x is going to be divided by 1. I know that it would probably be easier for some of you to just say x times 1, but I still want to go along with the idea of that b in the front you actually divide by. So I'm going to divide by 1, which really doesn't do anything at all, and then I'm going to take my y and times it by -2. So fill in your table and then check it against mine and see how you do. Hopefully we matched so far. So again, I just kept my x's the exact same way and multiplied my y's by -2. I'm going to do the same thing again. I'm going to set up the next value on the table, and then I will pause again in between actually filling them in, so you can pause and check with me. So as you see, I've set up my table. So now remember, with the x's you always do the opposite of what you see. Looks like -1, so I'm going to add 1, and then with my y's you do exactly what you see. Looks like add 3, so I'm going to add 3. So pause now and see if you can match my table. So here's my final table in the transformation. I still want to write the original f of x as my mother function being mapped to my h of x function as well. But these are the final results that you should have. So let's go ahead and just set up our final table then, and we can start graphing and identifying some important information. So I now have my final table mapping the mother function to my h of x transformed function, and I went ahead and just set up my graph as well. So let's go ahead and plot those points. Remember that it needs to look like an exponential, so if it doesn't have that curve and that asymptote that you're expecting, chances are you made a mistake. So I'm going to go ahead and plot this, and I'm going to wait on the asymptote. You and I can take a look at that equation together. So now I have my points plotted on my x and y axis. Notice that I labeled my increments by 1s. Whenever you're graphing anything, please make sure that you're clear on your increments. Alright, so taking a look at this, it has that nice curved graph that I expect. And remember, with an exponential function, I'm always going to have a horizontal asymptote. You can plug in whatever x you want, so there's no restriction on the domain, but there is going to be a restriction on the range. If we take a look at the equation over here, you always need to just look in one spot, and it is that value at the very end. Whoop, that's a little dark. Let's get rid of that. It is this value down here at the very end. That is going to tell you where your horizontal asymptote is going to be located. So keep in mind that it is horizontal, so it's going to be y equals. So our horizontal asymptote, or our HA, is going to be y equals 3. So let's go ahead and put that into the graph as well. So going up here to 3, remember that a horizontal asymptote is a dashed line, or an asymptote is a dashed line. And once we have that in, we can go ahead and just try to make it look as nice and smooth as possible. Then That's going to give us our sketch. Now we just need to identify a couple more things. So, I know the directions only said to explain the transformation, but we are actually going to be asking you to do more than that. So horizontal asymptote, y is equal to 3. There is no vertical asymptote and there's no hole in this graph. I also want to be able to find the domain and the range. So if I take a look at this, the domain, as I just said a minute ago, there's no restrictions on this. You can actually plug in whatever you want for x. But the range is going to have that restriction. Remember, we always go small to big. So it looks like the range on this is going to be from negative infinity as close to 3 as we can get without actually getting there. The next thing that I would probably like to find are x-intercepts and y-intercept. Well, the y-intercept is nice because it's actually in my table. So if I wasn't in my table to find a y-intercept, all I'm going to do is plug in my plug in x equals 0. So if I go back to my table, it looks like for my h of x, I get 0, 2 as my y-intercept. My x-intercept might require a little bit more work. So to get my x-intercept, I'm going to do the same thing that I would have done for my y. I'm just going to plug in 0 for the other variable. So let's take a look back at the original function, and let's put 0 in for y and then manipulate. Okay, so to solve this equation, I went ahead and plugged my 0 in for y. Now I just need to get the exponential by itself. So I'm going to subtract the 3 first, and then I am going to divide by that negative 2 coefficient out in the front. So that's going to give me a negative 3 divided by a negative 2 is just a positive 2. And I get 2 to the x minus 1. So I just moved the minus 3, moved the positive 3 over by subtracting it, and got rid of that negative 2 out in front by dividing it. Now, in order to do this, you're going to have to use logarithms. So I'm going to log each side. I'll get log of 3/2 is equal to, bring that exponent down, that's why we're doing logarithms in the first place, and then divide, and looks like add 1. Now, there are a whole bunch of different ways that you could clean this up. I'm not a big fan of fractions in fractions because I just don't think it looks very good. So you could actually do that second property of logarithms where division is really subtraction, or you could rewrite this using change of base formula. So I think I'm going to go ahead and rewrite this using that second property of logs and then put that down as my intercept. So again, as I said, this can be done multiple ways. This is how I choose to let my answer look so I don't have fractions and fractions. Again, you could have done this change of base, you could have actually divided. There's a couple ways you could do this. Alright, so we've got x-intercepts, y-intercept, domain, range. We have our asymptotes. I think we also need to know the actual explanation for this thing. So let's start explaining off to the side. I'm just going to go through my table one little piece at a time. So the first thing that I saw was that I took my x's and I divided by 1. That doesn't really do anything, so I'm not even going to talk about it. I took my y's, though, and I multiplied them by a negative, which means I reflected my y's. To reflect my y's, it's the y direction, so this is a vertical reflection. So that's one of them. Then I not only times by a negative, but I times by a negative 2. So the 2 is going to take the y values and actually stretch them out, so it's going to make them further apart. So I get a vertical stretch. Alright, that takes care of the timesing by the negative 2 on the y's. Then it looks like with the x's I needed to add 1. Well, when I take my x's and I add 1 to them, that means I'm actually shifting them to the right 1 unit. And then that plus 3 at the end means that my y's are actually going up by 3 units. So we've got their explanation of our transformation, we've got our sketch, we've got our points, and we've got some other pertinent information. Okay, the next problem we have has to do with compounding continuously, and what's actually kind of nice about this, I know you may be grumbling a little bit because you had to do monthly, yearly, daily, all that business last year. The only type of compounding you and I are going to talk about at all this year is continuously. So it's always going to be that one formula. So it's the same formula from your notes, we just call it PERT. And just going to plug stuff in where it belongs. So let's identify the information that we've got here. So 4729 is invested in an annual rate. All right, if that's the investment, then that means that this is going to be the P. This is the principal amount. E is just E, Euler's number. You don't plug anything in for it. R is going to be our annual rate, so the 2.9%. This is going to be our R, but remember we're going to have to turn it back into a decimal. And then T is 13 years. So we have everything that we need. Now all we have to do is plug it in. So let's take our formula out, which is going to be A is equal to PERT. Plug stuff in where it belongs. So our P was going to be 4729. E is just E, leave it as Euler's number. And then our rate, we need to go ahead and change that 2.9% into 0.029. And then times, T is going to be my time in years, which is 13. At this point, for this whole problem, all you need to do now is grab your calculator and type it in. So when I typed this in, my calculator gave me 6894.4294. Now this isn't what I would give as an answer, because having that much change doesn't really make any sense. So, but I do need to think about this in context. I invested this money. If I go in to take the money out of the bank, typically what the banks do is they will truncate after the second spot. They're not going to round up for you. That's not going to happen. So what I can actually withdraw, or what would be available to me, is going to be $6,894.42. So if it's money that's coming to me from an outside entity, such as a bank or a lender, I am going to get 42 cents. Now, if I was doing the charging, I would definitely round up and make it 43 cents. So, which is where banks kind of make their money. All right, let's move on to the next one. Okay, so the next question is more, just a little bit more practice with your calculator. So we've got an inflation problem, and it averages 4% over the next 10 years, and we already gave you an equation that models that information. So C of T is equal to P, it's present cost, 1.04, hopefully you see that, 1 showing the increase, and then the 0.04 showing the increase by how much, and then the T where we have T is time in years. So we have price of an oil change for your car is presently $23.95. Use a graphing utility to graph this function. So what I did was I went ahead and typed it into my Y equals button, and I went ahead and hit Z standard or zoom standard like I normally would, and I didn't see anything. So what I decided to do was I changed my window a little bit. So my recommendation to you on this one is you're going to go to your Y equals button, your Y1, and you're going to type in present cost is going to be $23.95. Open a set of parentheses, 1.04, close the parentheses, hit the caret key, and then use your XT theta N button. If you hit zoom standard on this, -10 to +10 isn't going to show you anything at all. So I went ahead and changed my window. So I went to my window, and I started thinking about what this really meant. Well, it wouldn't make any sense for me to think about going back in time for my x's, but I did want to see the x-axis, excuse me, the y-axis. So I did my x min at -1. And then I did my x max at 20. Because I know the next question down asked me to take a look at the 10, so I wanted to see it. For my y min, started thinking about money again, so I'll do -1. So I just want to be able to see the axis. And then for my y max, I figured I'd go 100 and see what would happen. So the graph doesn't necessarily look exactly like what I want it to look like, but at least I can see some sort of a curve. So for me, I have this real thick y-axis, and that's just because of the increments that I've chosen. And I see a graph kind of curling up just a little bit. So I just kind of see this curl happening, real light curl. Almost looks like it's a straight line if I zoomed in a little bit further. So I have it, and really the idea of this one is just to be able to zoom in and zoom out, change your window so you can see what it is that you need. All right, so let's move on to the next slide then. So next slide is doing things algebraically. So we want to approximate the price of an oil change 10 years from now. So if it's 10 years from now, then that means that my x, in this case, which is my t from my equation, is going to be 10. So to do this, all I'm going to do is go to the table. So I'm going to hit my table, and I'm going to scroll down until I see x is equal to 10. And then I'm just going to take the approximation straight out of the table. Let's see what that is. So if I hit my table button, need to move down or move up as necessary, move down a little bit, and it looks like after 10 years it has my y being 35.452. So in 10 years, my expectation is that it's going to cost me $35.45. So that's from my calculator, just using the table. It says approximate. Well, the best you can get is the approximation. You could even hit the trace button on your calculator and see if that'll help you. All right, next slide. We want to verify the answer to be algebraically. So what we want to do is plug in 10 for the exponent, because that's the time. So we're going to do the cost after 10 years. I'm going to take my equation, which was 23.95, quantity 1.04, which is the increase, and then my exponent is just going to be 10. So now all I do is type this into my calculator. So if I type this in, let's see how close my approximation was. Not too bad, actually. In my calculator, C of 10 comes out to being approximately 35.4518. So then I would still truncate or round this to 35.45, which matches the previous slide from my table.